Hello everyone, welcome to lecture 22. So today we will talk about the geophysical parameters of snow. So we have learned about the cryosphere and cryospheric related hazard. So the geophysical parameters have been proved to be an important source of information and that are used in multiples of hazard analysis, right. So we will try to understand the geophysical parameters, what are they and what is their impact on the glacial system. So solid precipitation is the main source of mass for glacial system. We all know that. The geophysical properties of snows are essential to study the snow glacier system and can be used as an indicator for any related hazard. So how they are serving as an indicator, that we will understand slowly. The important geophysical parameters of snow like dielectric constant, density and liquid water content plays a vital role in avalanche studies, hydrological modeling and flood monitoring. Studying snow geophysical parameters demands the continuous monitoring of snowfall and snowpack characteristics, because unless until we do not have the complete information about the snowfall and the snowpack characteristic in terms of geophysical parameter, we will not be able to characterize a particular system. This requires in situ measurements, which are also necessary to evolve a robust model for estimating snow geophysical parameters over the time, right. So we all know that in situ measurements are the only way we can have the accurate values, right. But since we are talking about the glacier and glacial system, these terrains are very rough, right. So it is very difficult to reach and collect the information all the time in different seasons. So that is why particularly in hilly terrain, the in situ measurements are challenging and expensive. To retrieve the geophysical parameters of snow, we will need to locate a reliable source of information, and here the role of remote sensing comes into the picture, right. So the geophysical parameters of snow are crucial for wide range of scientific and practical applications impacting various fields starting from climate science to hazard management. And the importance of geophysical parameter of snow can be seen in many of the areas like hydrological modeling, water resource management, climate and energy balance, hazard assessment and prediction, ecosystem and biological processes. So everywhere the role of geophysical parameters are very important. So the geophysical parameters of snow such as albedo, density, wetness and grain size are crucial for understanding and modeling the snow glacier system, climate change and hydrological processes. The geophysical parameters directly influence surface energy budget. We will understand this when we will talk about the parameters, hydrological cycle and the overall health of the mountain ecosystems, right. So when we talk about the geophysical parameter and when we define the snow, it is usually restricted to the material composed of air and ice that has not changed much since it fell on the ground, right. When we talk about geophysical parameters of snow, that encompass a range of intrinsic physical properties that dictate its state and evolution, and the snow cover properties or the snowpack properties are broadly classified into optical, electrical, mechanical and thermal, right. So here we have optical property, electrical properties, mechanical properties and thermal properties, and the reference is given here so that if you are interested you can refer to these papers and you will get very detailed information about these properties. And remember, these parameters are not static, rather they are highly dynamic in nature, undergoing continuous transformation, right. So that is why these geophysical parameters need to be monitored throughout the time, so that we will have the complete understanding about the system. When we talk about the optical properties, let us try to understand the spectral signature of snow. So here you can see the different snow spectras which is captured in Arunachal Pradesh. So here we have fresh snow, coarse grained snow, clean snow, wet or impure snow, and then edge snow. So we have collected the information, and then you can see how they are behaving in different electromagnetic wavelength range, right. So the spectral signature of snow is characterized by high reflectance in the visible spectrum and lower reflectance in the short wave infrared region. The snow shows high reflectance in the VNIR range, which is 400 to 1000 nanometer, which decreases with aging, impurities, or the presence of liquid water due to changes in its microstructure and increased absorption. In the SWIR range, right, so here snow shows low reflectance due to strong absorption by ice and liquid water, aiding in remote sensing based snow type classification. So because of these absorption features and their change in the intensity, we can easily identify what type of snow we have or what type of grain sizes we have. So that can be identified using these optical properties. When we talk about the electrical properties, so these are primarily governed by its liquid water content, temperature, density, and impurities, and are typically described in terms of dielectric constant, which is nothing but the permittivity, and the electrical conductivity. So we will have the detailed discussion on this. So this is just the basic information. So the snow permittivity is one of the important electrical properties of snow, which varies with electromagnetic frequencies. And remember, here I have given some of the very important references. So in case if you are interested, you can refer to these papers. These are very nice paper and they have detailed information about these properties. Snow dielectric properties, including dielectric constant and dielectric loss, are influenced by density, moisture, and microstructure. So the electrical conductivity of snow increases with liquid water content, temperature, and impurities like salts or soot, right, which enhance the mobility of ions within the snow matrix. So now you understand why these electrical properties are important, because these are the indirect measure of what is the status of your glacier system, right. When we talk about the mechanical properties, the mechanical characteristic of snow are primarily investigated for their role in avalanche initiation and mitigation. Additionally, they are crucial for addressing practical challenges such as vehicular mobility, snow clearance, and infrastructure development in snow covered environment. And the main requirement for this mechanical property, we have the constitutive equation, that is relations between the stress tensor and the motion, and the second one is the fracture criteria, which limit the reason of validity of consecutive equations, right. So the tensile strength of ice varies between 0.7 to 3.1 megapascal, and compressive strength varies from 5 to 25 megapascal over the temperature ranges between -10 to -20 degrees Celsius. The tensile strength of ice decreases with increasing ice grain size. The ice compressive strength increases with decreasing temperature and increasing strain rate, but ice tensile strength is relatively insensitive to these variables. Snow is an open cellular form of ice. Both the strength and fracture toughness of snow are substantially lower than those of ice. So these mechanical properties are very important, especially when we are talking about the snow avalanches or maybe the ice calving. So these can give you the more information about the target snowpack. The thermal properties of snow particularly its low thermal conductivity and high insulation capacity govern the heat exchange between the atmosphere and the ground. So, remember I talked about the surface. So, from here you have geothermal energy and from here you have solar radiation, right. So, and here if you have a glacier ice or the snow, it is basically very good insulator, right, and it is having the low thermal conductivity. Because of that, it is restricting the temperature changes in this particular system so drastically. That is why when you have any foreign material here, that will lead to change its thermal property, and then you will have major change in this glacial system. That is not ideal for our survival, right. So, that is why these thermal properties are very important when we talk about the stability of a glacial system. In avalanche science, these properties affect snow metamorphism, bonding between layers and weak layer formation. All of those are critical for avalanche forecasting. In permafrost modeling, snow acts as a thermal buffer, delaying or preventing ground freezing and thawing, thus influencing permafrost degradation. Understanding the thermal insulation properties of snow is essential for engineering design in snow covered region. So, if you want to construct a building or maybe a warehouse, then you need to have the complete information about this snowpack, where subsurface thermal dynamics directly influence structural stability of that particular area. Heat capacity of snow and freshwater ice at constant volume is about 3% less than constant pressure at the melting point, right. And the difference between Cp Cv, which is nothing but your constant volume and the constant pressure, decreases with decreasing temperature. So, I hope you have understood the implications of thermal properties on higher altitudes, right. So, the snow exhibit fascinating thermal properties that play a crucial role in its behavior and its impact on the environment. These properties are largely influenced by snow's highly porous structure, which traps air in between. So, I hope you remember this one. So, when you have a liquid, this is liquid water. So, from here if we are going towards this freezing, then what will happen? There will be release of the energy, and the energy will be 334 joule per gram. When it is from solid to liquid, it is absorbing the same amount of energy, and then when from liquid we are talking about the gas, so there will be evaporation, and here the energy will be absorbed, and the energy is 2500 joule per gram. Similarly, when gas is getting converted to liquid, then 2500 joule per gram, that energy will be released. And then there is a direct conversion also from gas to solid. So, here what you have to do, you have to add this energy plus this energy. So, together it will be 2834 joule per gram. That energy will be released and we will call it deposition. Similarly, when it is getting converted from solid to gas, so we call it sublimation, right. So, this sublimation will absorb 2834 joule per gram. So, this is very interesting, and that explains the thermal properties of this snowpack, and this relationship can be easily understood and it can be directly linked to the snowpack properties. So, when we talk about the remote sensing techniques especially used in the geophysical properties of snow, so here we have different parameters that we talk about. So, starting from snow grain size, then density, permittivity, wetness, depth, impurities, these properties are used to define the geophysical properties of snow, right. We will try to understand this one by one. So, when we talk about the snow grain size, So, grain size refers to the typical size of individual snow crystal or ice particle that makes up the snowpack. So, here you can see some of the examples of different types of snow grains, right. So, here it is very smooth, here it is again coarser, this is again much coarser than that. So, what is the impact when sun is illuminating this particular area? What happens? Depending upon the grain size of this particular target, the amount of energy will be released, right. So, this amount of energy depends on the size of the grains. So, that will influence the radiative total budget, and that will indirectly impact the energy which is stored or reflected by a snowpack. Then comes the density. So, the snow density is a fundamental property of snow defined as the mass of snow per unit volume. It varies significantly depending on the snow's age, condition and other factor. Fresh dry snow has a relatively low density, while older or wet snow can be significantly denser, because we are talking about the solid precipitation here. So, let us say we have a solid precipitation here, right. Then subsequently we have another layer of solid precipitation, snowfall is happening. Then because of the overburden pressure and the temperature, this particular layer will be compacted. So, the factors which affect the snow density are snow type, what type of snow, whether it is fresh or old snow, you will have different density. The temperature will also control it, the wind, because if you have high wind speed in this particular area, fresh snow to ice, that conversion will be fast. Then metamorphism, depending upon the overlying pressure, the metamorphism will start and then compaction will take place, and that will lead to the change in the density. Then we have liquid water content. What is the fraction of liquid water content in your snow? That will also define the density. Then we have permittivity. Snow permittivity, which is a measure of its stability to store energy in an electric field, is highly dependent on its state, whether it is dry or wet, and the presence of liquid water can be studied. The snow permittivity, which is a measure of its ability to store energy in an electric field, it is highly dependent on two things. First one is the state, whether it is dry or wet snow, and the presence of liquid water in this particular snowpack. Dry snow, primarily composed of ice and air, has lower permittivity than wet snow, which includes liquid water, because when it is a fresh snow, you have more voids in between. So, it is basically ice and air, but subsequently when it is getting converted to a particular layer with overlying pressure, what happens? It will have less space for the air, and the liquid water can also be present in between. So, the factor affecting snow permittivity are snow density, liquid water content, temperature, snow type, snow microstructure, which is nothing but your crystal size and orientation, that can be studied to know more about the permittivity. Then comes the wetness. Snow wetness, also known as liquid water content, refers to the amount of liquid water present within a snowpack. So, this is one example. Here you can see visually you can identify this is a dry snow and this is a wet snow, but this is just for the example. So, it is a crucial factor in understanding snow hydrology, seasonal snow change and regional climate variability. The presence of even a small percentage of liquid water significantly alters the physical, thermal and electromagnetic properties of the snow. So, what are the different factors which controls this snow wetness? So, they are temperature, solar radiation, air temperature, snowpack density, precipitation, slope and aspect. So, this precipitation I am talking about the normal precipitation, liquid precipitation, right, not the solid one. Then comes the snow depth, which is referred to the vertical distance from the surface of the snowpack to the ground beneath it. So, let us say this is the lowest layer and here you have a rock surface, right, a rock or soil which is present here. So, the depth will be this much only from the surface, but if there is another layer of snow, then this is not the depth, right. So, depth will be further down, and generally we have some mechanism to measure. So, there are some automatic way of measurement. For snow depth measurement, we have different approaches. One is the manual, another one is automatic. Manual, where we can use a scale and measure the annual or seasonal precipitation, and the automatic, where we are using some sensors to identify change in the elevation, so that we will be able to identify what is the precipitation value. Then comes the impurity, which is very important. Snow impurities refer to particles that are mixed into the snowpack, affecting its properties and ultimately its melting behavior. The presence and concentration of these impurities significantly impact physical, chemical and radiative properties of the snow. So, here you can see the example. Here this side is the fresh snow, whereas the surface it has some contamination, impurities, right. So, what is the major difference here? If light is falling here, the more amount of energy will be reflected, right. Whereas, if this particular area receives the energy from the sun, the less amount of energy will be reflected, right. So, here the difference between these two is the amount of energy which is getting reflected from the surface, that we call albedo. So, if there is a change in the albedo, it will significantly affect how much energy is getting stored in the glacier system. So, here if you see, here less energy will be stored, right, because maximum is getting reflected, but here more energy will be stored, and that will change the status of this glacier system. So, here more melting is expected. So, the common snow impurities that we see in glacier system or snow, those are black carbons or soot, dust which is nothing but your mineral dust, biological impurities which is algae, chemical pollutants which are coming through the air circulation, and the debris which are coming from the surrounding hills when we have the landslide and any other kind of geological processes. So, the impact of snow impurities can be seen in terms of reduced albedo, significantly affect the earth's energy balance, then increased snow melt, that is ultimately resultant of the snow impurities in terms. So, the increased snow melt that we can see if we have more snow impurities in a snow pack. As we all know that these snow packs are situated at higher altitude, where the field investigation and the in situ measurements are very difficult. So, that is why we have to find a alternative way, and the remote sensing is one of the very important source of information in estimating or measuring the snow properties. So, geophysical properties of snow. So, it helps to overcome the challenges in situ measurements of snow properties. Then particularly microwave remote sensing overcomes the problem of cloud cover as observed in optical remote sensing, especially in higher altitude areas. It also provides data or products for a larger aerial extent. So, these are the major advantages why we are talking about the remote sensing application in geophysical property estimation. So, now we will see the snow grain size. Snow grain size is a fundamental property of snow and is directly proportional to its surface area. Here you can see the example of snow grain size. Estimating snow grain size is crucial for understanding and monitoring the Earth's radiation balance, particularly in the context of the cryosphere. The size of the snow grains plays a key role in determining snow albedo, impacting the reflection of sunlight by the snow covered surfaces, right. So, here we have some references. If you are interested, you can refer to them and you can read more details about this basic. The snow grain size, which represents this course of snow metamorphism, has been identified as one of the most valuable snow physical parameter. The snowpack stability has frequently been examined in snow avalanche utilizing information derived from snow grain size and snow shape. Due to the rough topography of the Himalayas, particularly the Himalayan region, many geophysical parameters are poorly sampled because of the accessibility and the support, right. So, here as a result, developing sophisticated remote sensing technique is critical for obtaining timely information on the spatio-temporal variability of snow cover and snow grain size. According to IIHS International Classification for seasonal snow on the ground, the observer should select a homogeneous snow mass and record the mean size of its predominant grains with a focus on measuring the diameter of grains, which is its grain size, and it is typically measured in the millimeters. So, although this approach might work well for field research, in the case of remote sensing based research, characterizing the average snow grain size over wide range is necessary. Surface feature extraction and mapping based on spectral signature are popular hyperspectral remote sensing application. So, here we will try to see how hyperspectral remote sensing is being used in snow grain size studies. Snow surface features such as snow grain size, snow wetness and snow albedo have all been studied through hyperspectral remote sensing. The hyperspectral images and advancement in radiometric asomatic models have led to the emergence of more precise snow grain size inversion models. And here we will try to understand how hyperspectral remote sensing is used in snow grain size. So, here in this particular paper, they have used Hyperion sensor to retrieve snow grain size and spectral albedo and for the western Himalayas snow cover. This is from India. In contrast, Singh et al. 2022 employed Prisma data, right, for the snow grain size estimation. In another study, the inversion methods for snow grain size called the absorption band area method, which is hardly affected by topographic error, solar illumination, angle and noise that is being used. So, the physical sense of the method is that the absorption feature is directly proportional to the amount of energy absorbed by the ice particles over the spectral region. So, that we have seen in the hyperspectral remote sensing, how a particular characteristic wavelength absorption features are coming because of the presence of the chemical composition and their internal atomic structure. The same fundamental is being used here in different way to identify the snow grain sizes. SID is used to map snow grain size, and then the absorption band area method is utilized to validate the trend of energy absorbed by each snow grain size. The grain size mapped method is applied to Prisma data using JHU's snow spectral library, and for this South Lona glacial lake region has been selected because recently there was a GLOF event. So, it highlights the advancement in remote sensing technologies for snow research using hyperspectral data from Prisma level 2. This is level 2, so that is basically bottom of the atmosphere reflectance. In the lack of in situ data, this study sheds light on the possible use of snow grain size mapping to evaluate snowpack condition and dangers. So, with this I will try to explain you the basic details. So, with this I will end the part 1 of this lecture. We will continue this in the next lecture. Thank you.